we won't have to do this all over again next year. So what we have today is phase changes. What do I mean by phase changes? Huh? Electrical phase changes? What? Did you say electrical? Are you thinking about you can have electrical phase changes. That's a little bit advanced. That's like.
I said from like a liquid to a solid.
Oh, liquid. I thought you said electrical. Yes, a liquid to a solid is the exact phase change I'm looking for. Electrical phase changes are something completely different. So phase changes from a liquid to a solid. What else? What other phase changes can you have?
Solid to a vapor.
Solid to a vapor or gas, and then what's the third one?
Liquid to a gas.
Liquid to a gas. Well, technically there's 6, right? Because you got solid, liquid, gas. You can go from solid to liquid, liquid to solid. You can go from liquid to gas or gas to liquid. And then you can have the weird one that we don't do very often, which is solid straight to gas or gas straight to solid, skipping the liquid phase in between. The whole point of today, what they want to talk about, they're going to get into a little bit of solid, liquid, and gas, but we've already talked about that in a different chapter. What they really want to talk about is the intermolecular forces. What causes a solid to be a solid? What causes a gas to be a gas? And the whole idea behind this is intermolecular forces, which are the attractive forces in between molecules. So what makes a piece of ice stay together where water can just flow around? The ice literally has more attraction in between the water molecules than the water does. In the ice, the attraction is so strong, the molecules can't move past each other. They can't swirl around. They can't change position. They're like locked into place. In a liquid like water, they have a little bit more movement. They're still connected to each other. There's some attraction between them. So they can slide past each other, but they're not going to separate. If I go all the way up and decrease the intermolecular force all the way to like a gas phase, at a gas phase, there's almost no attractive forces between water molecules. They're spreading out, they're in steam now, and they're out in the air, and they're going to move around like a gas. So when they come together, they're not going to be attracted to each other. They're just going to bounce off of each other and continue on their way. And so as we look at solid, liquid, gas, know that they're relating it back to how strong the atoms are pulling at each other. And the idea is, if that attractive force is really, really strong, they're held together really tightly, they can't move past each other, they're going to be a solid. They're going to be stuck in the same position, which is a solid. If you decrease that a little bit, you get down to a liquid. If you decrease it all the way, you get down to a gas. So substances with the strongest intermolecular forces are solids. Substances with moderate intermolecular forces are liquids. And then if you bring it all the way down where you have almost no intermolecular force, your atoms can just leave each other whenever they want and become a gas. So they kind of have that illustrated here. You have gas where your molecules don't really have any attraction. They're going to get as far away from each other as possible. A liquid where they are attracted to each other. They're going to stay next to each other, but they can still move around. They can move to any other molecule and feel that attraction. They're not paired up and like in this solid combination. Then I increase my attraction even more. Now, not only are they attracted to each other and they're really close to each other, but they're going to get locked into place where they can't even move around. They can't go visit other atoms or be connected to them. They're only connected to the atoms that they're already connected to. So those are your 3 phases, solid, liquid, gas. And we're looking at that as far as attraction, how much the atoms attract each other. So gas phase molecules have enough kinetic energy to overcome that intermolecular force. And that's why a gas is all spread out. There's a little bit of attraction between these molecules, but any kind of force, any kind of temperature increase is going to put enough kinetic energy in here where that attractiveness is just overcome. The atoms just kind of zoom off into the air and they no longer feel that attractive force anymore. Let's see. Molecules of substances have greater intermolecular forces than others. So they're basically showing you here Why does fluorine and chlorine exist in a gas phase at normal temperatures and not a liquid or a solid phase? Well, the reason is this is the intermolecular attractive energy line they have right here, the average kinetic energy at 298 K. These two, bromine and iodine, which are liquids, have more of that intermolecular attractive force. So when they're all sitting around next to each other, they want to group up. They want to clump up because they're attracted to each other. That's going to make them a liquid. Where these two gases, fluorine and chlorine, have very low attractive forces. So at normal room temperature, they're not really attracted to each other at all. They're not going to hang out together. They're just going to go into their own separate parts of the room and become a gas. So it's all about how much attractive energy you have, or that intermolecular force that you have. So let's see. They're just basically going through what I just said. Now, dispersion forces. Dispersion forces are the intermolecular forces caused by instantaneous dipoles created by the movement of electrons and molecules. The idea here is, in an atom, we talk about sharing electrons, and a certain number of electrons are on one atom and a certain number of electrons are on the other atom. This is the idea that because those electrons are moving, there will be points in time where one atom has a whole bunch of the electrons and it's going to have a whole bunch of the negative charges, and the other atom is going to have more electrons, or, well, it depends on which one you're talking about. One of them is going to have less electrons, the other one's going to have more electrons. That's going to change their charges, and so I can have a molecule like, for example, a water molecule, H2O. It has one oxygen in the middle and two hydrogens out to the sides. And the idea here is, even though they share electrons in between them, the oxygen is going to be more negative and the hydrogen is going to be more positive. And so the dispersion forces are the idea that as the electrons move around, they're just going to hang out in a certain area of the atom, and it's going to make it become more positive or more negative. When I get that, I have atoms that are called dipoles. And what I mean by dipole, it has a positive and a negative pole. It's got a positive end and a negative end. Sometimes that might move around. Sometimes it might stay in the exact same place. It just depends on the atom. So dipoles are opposite charges separated by a distance. So they show a couple examples here. We have atoms that have a positive end and a negative end. And that's the whole point of a dipole. Dipoles that cause dispersion forces are the result of attraction between positively charged nuclei and negatively charged electron clouds of nearby molecules. So what does all this mean? Dispersion forces increase as the number of electrons and molecules increases. Fluorine and chlorine are gases at room temperature. Because they have more electrons, that means they have more dispersion forces. So these positive and negative ends are going to kind of push each other apart and make your substance more likely to be a gas. It's dispersed. So bromine is a liquid at room temperature, and iodine is a solid at room temperature because of the different dispersion forces acting on them. So you can see here, I have boiling point, I have number of electrons. The chemicals with low electrons have low dispersion forces, and so they are gases. As I go higher and higher numbers of electrons, I go up into a liquid and then into a solid. So they tell me iodine is a solid, bromine is a liquid, and chlorine and fluorine are gases at room temperature. And so they're relating the number of electrons to dispersion forces. Molecules with a greater number of electrons have higher boiling points and higher dispersion forces. So dipole-dipole force is the intermolecular force caused by attraction between dipoles with polar molecules. This occurs when one more positive side of one polar molecule is attracted to one more negative side of a polar molecule. As strengths of dipoles increase, attractions between dipoles increase as well. So what are they getting at here? Carbon monoxide. Dipole-dipole forces explain why carbon monoxide, CO, is a higher boiling point than nitrogen. Even though they have similar dispersion forces, The CO has both dispersion and dipole-dipole forces, so it's going to have a different boiling point. This is a little bit advanced. I'm telling you right now, we're not going to get into anything too crazy with this. It's just a bunch of multiple choice questions, like word-based multiple choice questions. There's not a lot of math here. So hydrogen bonds are a type of dipole-dipole force, not covalent bonds. They're going to ask you a couple questions about hydrogen bonds specifically. So know that they're not covalent bonds. They are a type of dipole-dipole force, which means hydrogen bonds are really like a bond between a positive and negative charge, almost like an ionic bond, but a little bit different. So a hydrogen bond is a strong intermolecular force between an electron-deficient hydrogen and a highly electronegative atom that has at least one or more lone electron pairs. So basically, what are they saying here? A hydrogen bond is a force between an electron-deficient hydrogen. So a hydrogen that doesn't have enough electrons and an electronegative atom that has at least one lone electron just sitting by itself. So basically, this bond is when I have a hydrogen that doesn't have enough electrons and another atom that just has an extra electron sitting around. Those forces, they're both going to kind of use each other and form a hydrogen bond in between. So this can only occur in molecules in which hydrogen is bonded to one of these very electronegative atoms, nitrogen, oxygen, or fluorine. So what they're telling you here, they're going to ask you a question about a hydrogen bond. You want to look for hydrogen combined with nitrogen, oxygen, or fluorine. If it's not combined with one of those three, it's probably not a hydrogen bond. So here's their example. They have the hydrogen-fluorine bonds here. They're bonding hydrogen and fluorine together. Here's another one, methanol. You have hydrogen bonded probably with your oxygen there. So that exhibits hydrogen bonding. So what do they say? Nitrogen, oxygen, or fluorine. Here's some more hydrogen bonds. It just gets crazier and crazier in a big 3D network. Now, we get to the very end. This is the part we've all been waiting for, trying to get to, our different phase diagrams. So a phase diagram is a diagram showing the phases in which a substance exists over a wide range of temperatures and pressures. It will show you the solid phase, the liquid phase, and the gas phase for all the temperatures and all the pressures that you can get to. So here's your example of a phase diagram. Notice here, I have pressure. So on the low end, I have low pressure. On the high end, I have high pressure. On the bottom here, I have temperature. So low temperature is going to be towards the left. High temperature is going to be towards the right. So this kind of makes sense. When my temperature is really, really low, what is my water phase? What phase is my water in when my temperature is really low? Solid. It's ice, right? So when it's below 32 degrees Fahrenheit, my water is solid as ice. Then I increase the temperature. What's going to happen to my water? It's going to turn into a liquid. And then I increase the temperature even more. What happens to the water? It turns into a gas. Now, we don't see water go straight from a solid to a gas very often, right? It's difficult to turn ice directly into steam. Usually you have to melt it into water. But if you look down here at low pressures, I can have my water go straight from a solid directly into a gas and skip the liquid phase altogether. So if the pressure is low enough, I can do this sublimation deposition where I skip the liquid phase, go straight from solid to gas. Over here, I can actually change my state from liquid to gas by changing the pressure, but not the temperature. So if the temperature is the same, like right here along this red line, my temperature is not moving, but my pressure is dropping. That's going to change my state. The other thing I'll point out is the triple point right here. If you can get to this pressure and this temperature for that specific chemical, in your beaker, you will have solid, liquid, and gas in all three phases. It will basically be alternating between ice, boiling, and regular liquid all together at the same point. So when they mention the triple point, you're going to have solid, liquid, and gas all together in the same beaker because you have the right pressure and everything. So normal freezing point, normal boiling point, triple point. What they mean by normal, that's your STP. It's going to be at 1 atmosphere pressure. That's your standard outside pressure. So if I'm at 1 atmosphere pressure and I boil water outside or I freeze water outside, those are my normal or boiling points or freezing points. The triple point is where they can all exist at the same place. And if we go back just real quick, there's your normal freezing point. There's your normal boiling point because it's at 1 atmosphere pressure. And then your critical point. Critical point is the point beyond which the vapor phase and liquid phase cannot be distinguished. And what they mean is, where are we at? If I go back to the map here, here's your critical point. At a certain pressure, you can't really figure out, is it a liquid or is it a gas? They're both going to behave the same way because at this pressure, my gases are squeezed down enough where they're almost like the liquid phase. And so it's very difficult to tell the difference between the two. So that's why that arrow just kind of stops right here. It's hard to find that line exactly where it exists. And then I believe that might be all. The intersection of temperature and pressure values on the diagram, if a substance is solid or gas. They will do a couple of those, just so you know. They will give you this chart. They will tell you a temperature and a pressure for your chemical and then ask you, well, what do I want to do if I want to get it to a solid? Or what do I do if I want to get it to a gas? And you'll have to tell them, oh, you got to lower the temperature. Or, oh, you have to raise the pressure. That will get you to a gas. So keep an eye on that and use this map. Go ahead and open up the assignment and get started on it. It's a lot of questions, but they're all multiple choice, and it shouldn't take too long. I will go ahead and post